Okay, in this video we will continue with our circular reasoning with right angle trigonometry. We'll kind of just run through several problems here. If you search on Google, you should be able to find the worksheet that's associated with this presentation. Just search on Google for right angle trigonometry and then put KUTA for CUTA, and you should be able to find this worksheet. You can screenshot that and find it. It should give you both a worksheet and a key. So this is the worksheet. I'll post a link to it. Anyway. The second problem is right here. We're supposed to find the angle given two sides, and we'll do that more or less in a straightforward way and see what we can use our compass for as we proceed. For this video, you'll need a straight edge, a pen or a pencil, and a compass. I like to get the Statler compasses that you can put a pen or a pencil into, instead of ones that come with a lead point already inserted, because what happens when you run out of that lead, right? Okay, so for problem number 2, we will draw the problem, represent it graphically on our workspace to the best of our abilities. And we were given that this side is 13 and that this side is 4. So what we're looking for in this problem is the angle theta. Before we find that angle, let's insert our pen into the compass that we have. Make sure it's straight. Okay, and now this is the key point. In all of these problems, you want to set your compass diameter, which is the radius, equal to the length of the longest side of the triangle, which would be the hypotenuse of the triangle. Right? And then you want to put the pointy end at the vertex of your reference angle. So in this case, I'm going to put the pointy end right there, and then inscribe in a full circle all the way around just like that. And now we can sort of go to work. So if we recall, the radius of a circle is the hypotenuse of a triangle. This is my reference angle. This is where I'm looking from. So opposite of my reference angle is the sine of theta multiplied by the radius, which I don't yet know, but I will in a moment. The adjacent angle, which is the one that's kind of right next to the reference angle, sorry, the adjacent side, which is right next to the reference angle, is the cosine of the angle theta multiplied by the radius. So it would be very helpful if we could discover what this hypotenuse length is. I don't need to do that in order to find out what this angle is, and I'll tell you why in a moment. But it would be nice, and it is possible since we have both sides. We might as well use the Pythagorean theorem to find this side, which we'll call C. We'll call this side B, and we'll call this side A. So C is the radius of the circle. It is also the hypotenuse of the right triangle. All right. So C equals the square root. This is just an application of the Pythagorean theorem. The square root of a squared plus b squared. So in our problem, that's the square root of 13 squared and 4 squared. Right? 13 squared is 169, and 4 squared is 16. And so we want to add these together. 16 and 169. So let's just quickly add those together. And I get 185. So what I'm looking for is the square root of 185. Is equal to C. So let me take the square root of 185. Now let me double check that that is in fact the square root of 13 squared plus 4 squared. Okay, verified. So in this case, C, or the radius of this circle, is 13.60147051. So this is equal to 13.6. We'll just round it. Now, we have more choices. Now that we've found the hypotenuse, we have more choices with how we find the angle. And remember, there are several functions in trigonometry. The ones that find the angles is if you have the sides, if you have side lengths and want an angle. You use arc sine, arc cosine, or arc tan. And this is a function. This equals sine -1. So inverse sine, inverse cosine, or inverse tangent. And it really depends on what angle you want. Mr. Fly has joined us. That will guide you to which one of these is most efficient to use. Since we have all the sides, it doesn't matter. And I'll explain why. All right. So, in order to explain why, we have to remember what sine, put it this way. If I multiply the sine of theta times the radius, I will get 4. Okay? In this case, we know the radius. So the sine of theta multiplied by 13.6 equals 4. So if I want to know what the sine of theta is, I can't find out what I don't know what the angle is, but if I want to know what the sine of theta is, I just take 4 and divide by 13.6. And that value, and I'll use the full value here from the calculator, that value is 0.29. Okay, what's more important than that value right at this moment is what these represent. So in your book, and in most trigonometry books, this is the hypotenuse, which we now know is the radius, and this is the opposite side from the angle, the reference angle. So that's opposite over hypotenuse. Okay, that's SOH. Sine equals opposite over hypotenuse. In the same vein, cosine, which is C-A-H, from that mnemonic device SOHCAHTOA. Let's go back and think about cosine. So cosine of theta, which is this length, it's the base of this triangle. Cosine of theta multiplied by the radius of the circle equals 13. So since I know the radius, cosine theta multiplied by 13.6 is equal to 13. So if I want to know what cosine of theta is, I divide 13 by 13.6. Okay, and that what that actually evaluates to, cosine theta equals 13 divided by 13.6, and that gives me 0.95588233529. That's all well and good. There again, this side length right here is the adjacent side length, adjacent to the reference angle, and this is the hypotenuse, which we know is the radius. And that's where we get the ka part. So cosine is adjacent over hypotenuse. It's just not always presented clearly. Now tangent's a little bit different. Tangent is TOA, or tangent equals opposite over adjacent. So we have a lot of equivalencies here that get confusing. But tangent, it's not visible here. I can't point to it right here. It is the opposite side over the adjacent side. Another way of saying that is it's the sine divided by the cosine. I can't stress this enough. When you input an angle and you use this sine function, okay, this is the sine function. The output is a length. It's a distance. All right? So we're multiplying it by this scaling factor we're calling the radius. But when you put an angle inside those parentheses and you use this sine function, what comes out is a distance. As a matter of fact, when you put in an angle into sine and multiply it by 13.6, if you put in this, whatever theta is, if you put that in, multiply it by 13.6, you will get 4. Okay, 4 is this distance right here. Right? So visually, that is what you're getting. You're getting a distance. What you're getting is like the height of the triangle. If you think about this as the height, and this is the base, then you're getting the height of the triangle. So with the inverse function, okay, these are functions. With the inverse function, what you put in, instead of putting in angles, you put in lengths, right? And this always takes two arguments, separated by a fraction bar. All right, so what you put in there, the sine, you put in the opposite over the hypotenuse, or the radius. Okay, so in this case, you're going to put in opposite over hypotenuse. For cosine, you're going to put in adjacent over hypotenuse. And for tangent, you're going to put in opposite over adjacent. And for tangent, remember that's sine over cosine. Okay, so we're going to compute this out. We want to know the angle. So for arc sine or inverse sine or this function here, what you put in, you input length. And what gets output is an angle. So this is always going to be in degrees, what comes out of here. Degrees, degrees, and degrees. That's kind of like the opposite of these functions over here. Sine, cosine, and tangent. Arc sine, arc cosine, and arc tangent. It's kind of, you know, two sides of the same coin. This one, the arc sine or sine raised to the -1 there, the inverse sine, this is going to take in the opposite side and the hypotenuse side, the quotient of those two figures, and it's going to output an angle. Arc cosine will take the adjacent side length divided by the hypotenuse, or the radius, and it will output the same angle. And again, for tangent, the arctan, you put in the opposite side divided by the adjacent side, and in every one of these cases we should get the same angle, because are opposite adjacent are relative to our reference angle. So they would be different if we were looking at this angle over here, but we're looking at this angle. So with respect to this angle, this is the opposite side. With respect to this angle, this is the adjacent side. Okay. With respect to this angle over here, now this becomes the adjacent side and this becomes the opposite side. So I actually don't like using those terms very much. I like base and height better. I like to think visually, but maybe whatever works for you. So let's actually compute it. My opposite side is 4, and my hypotenuse, which we found, is 13.6. Trying to get this calculator out of the glare of that light. Let's see. Maybe unsuccessful. Okay, there we go. So let's actually compute it, and I'll show you what I'm going to be hitting here. I can't put the whole calculator in frame unless I turn it sideways. Is second, and then we'll compute the arc sine first. Second sine, and that gives me that arc sine symbol. Now that's a function. Open parentheses, give me arguments. Okay, feed me arguments. And what it wants you to feed, what this wants you to feed it is, it wants you to feed it the opposite side length over the hypotenuse length. Okay, so we're going to feed it the opposite side length divided by 13.6. Well, I'm going to go ahead and use that value we found using the Pythagorean theorem. And if I have this in degree mode, which I do, degree mode, if you don't, you hit mode, and then you go down to where it's highlighted on radians, cursor over, and then hit enter, and it'll turn it to degree mode. Otherwise, the output won't look right. Then hit second mode to quit and go back to your calculation screen. Now go ahead and enter on this, and you will get an angle. You'll get 17.1027, whatever. So let's record that. We got 17.103, we'll round, degrees. Okay, so this is redundant, but 17.103 degrees. For if I wanted to use different numbers, like this 13, if I wanted to use this 13 divided by 13.6, remember that gave us the cosine value, the cosine theta value for a unit circle of radius 1. That's what it gave us. But here I'm going to put in, I'm going to hit second cosine, and then put in 13, that's my adjacent side length, divided by the hypotenuse, 13.6. Remember, I'm going to go ahead and grab my value that I computed using the Pythagorean theorem, this one. Okay, close parentheses, and we should get 17.102728997 again. We should get the same thing again, and we do. So these were supposed to be the same. 17.103 degrees. Finally, for the arctan. You know, arctan is, to me, the least, you don't actually need it. It's the least visually understandable because it's asking me to put in the opposite side and the adjacent side, or the sine over the cosine. So I'm going to put in the opposite side length of 4, so I have to hit second tan, put in the opposite side length of 4 over the adjacent side length of 13, close parentheses, and again I should get the same angle again, and I do, 17.103. Okay, now in this problem I'm guessing what they wanted you to do was to say, uh-oh, I was only given the adjacent side and the opposite side. Therefore, I should use arctangent to find the angle. And we could have computed this thing in 2 seconds by simply hitting second tan 4 division 13 close paren enter, and it would have spit out, if we were in degree mode, it would have spit out this equals 17.103 degrees. If we compare that to our answer key, we see that on the answer key it says the angle is 17.1. Fair enough. Okay, so if this is 17.103 and that's 90, what is the other angle? Okay, well that's easy to do. We're just going to hit 180 minus 90 minus what we found. So this is 72.89727. So this angle here is 72.897. The problem didn't ask for that. The problem asked for this. So that's your answer to that problem, number 2. Let's look at the next problem. For the next problem, we are given this triangle right here. Right? Again, it's a right triangle. So let's draw it. It's a weird looking triangle. Okay. So in this triangle, we are given this information, and we're told that this side length is 6, and this is the angle we want. So here's our reference angle, and this side length is 9. So just based on this information, what is your hypotenuse and what is your base? No, I'm not sure that it's entirely clear. The way I drew it makes this look like the hypotenuse, and it does appear to be the hypotenuse, but I'm not sure. So what can we do? Let's just take a moment and evaluate what we know. I know that whatever this is the hypotenuse or this is the opposite side, I know that this is the adjacent side. So this is definitely the adjacent side. ADJ ACENT, adjacent side. Okay, so whatever this side is, it definitely cannot be the opposite side because that's the adjacent side. So this would also be an adjacent side, right? But this is the short side. We know that because this is 6 and this is 9. So one of these has to be the opposite side, one of them has to be the hypotenuse, and one of them has to be the adjacent side. This is for sure the adjacent side. And you can't have an opposite side and an adjacent side share the same vertex here with the reference angle, because with respect to the reference angle, both of these sides are adjacent to the reference angle. So this must be the hypotenuse. Okay, this must be the adjacent side, and that, remember, the adjacent side length is the cosine, and I won't write that yet. Actually, don't want to write that yet. But that means this side over here is the opposite side. With respect to this angle only, it's not always the opposite side. If I was taking measurements with respect to this angle, which I could do, this would then be the adjacent side, this would stay the hypotenuse, and this would become the opposite side. But again, we are looking from here. That's why I draw the little eyeball, so you can know for sure that only with respect to this reference angle from this vantage point, I'm looking across the street here at this opposite side. And now let's take our compass, put the pointing end at the vertex of the reference angle, and then scale down that radius until you are the diameter of your compass is equal to the length of the hypotenuse of this triangle. And now inscribe your circle. That whole deductive reasoning that we just did is important because sometimes these triangles aren't drawn to scale. And maybe the side length representations visually are wrong. So you kind of have to go by the numbers, and you have to think about where you're looking from. Okay, now that we've done that, take your straight edge and lay it against the adjacent side, and then put a dashed line between the edge of the circle and the vertex of the right angle. Okay. Now the reason I did that was to show that this whole length right here together is the radius. So this is the radius. And just to reinforce that point, if I then rotate this down, this also must be the radius, right? So this hypotenuse, again, reinforce this point 1,000 times. The hypotenuse length is the radius of the circle. Okay, so because we have now put this in terms of a circle, we don't have to deal with adjacent and opposite anymore. I know for sure that this is the radius. Okay, here's the radius. And if this is the radius of the circle, the horizontal length, this length right here, this is the cosine. So I'm going to call this the cosine. And this opposite side, which we don't know, is the sine. Okay. You say, well, that looks confusing. But if you spin the circle around, we can think of this as the height. Okay, now I'm thinking this is vertical, right? So this is up now. So there's the height of a triangle. Here's the base of a triangle, right? And there's this whole circle around it. We can see then that this horizontal distance, this lateral distance here, is the cosine. This is the sine, right? This is the radius or the hypotenuse. It's just been turned. Okay, now let's compute. We could use the Pythagorean theorem to find the length of the sine. Okay, but we could also just remember that we're given the adjacent side and the hypotenuse, and so we could use the inverse cosine, cosine -1. Okay, this is also called the arc cosine. And we open paren that, right? And it wants two values in there. It wants the adjacent side length, and it wants the hypotenuse length. And remember what it's going to output. This is going to output the angle theta in degrees, if we have our calculator in degree mode. Okay, so let's actually stick values in there. So arc cosine, or inverse cosine, open paren, use the adjacent side length of 6 and the hypotenuse length of 9, and this is going to output an angle. Here's my calculator. Turn this guy on. So we're going to, remember, we have to be in degree mode, which we are. We're going to hit second cosine to get that inverse cosine or that arc cosine, and then we're going to divide 6 by 9. Close paren. And we get an angle of 48.19. Okay, if you round up on the hundredths place, 48.19. Or 48.2 if you want to round to the tenths place. So this equals approximately 48.2 degrees. That matches our answer key, right? We could have used the Pythagorean theorem to solve for this missing side. If I call this side A and this side B and this side C, right? I have the Pythagorean theorem, A squared plus B squared equals C squared, right? So if I want to solve for missing side B, I can do that. I say B squared equals C squared minus A squared. I just subtracted the A squared over here and over here. A squared and A squared. Okay, so B squared equals C squared minus A squared, so that means B equals the square root of C squared minus A squared. And that we plug in our values now. That means we're going to take the square root of 9 squared minus 6 squared. That means we're going to take the square root of 81 minus 36. Okay, good opportunity to practice subtraction. 81 minus 36. Okay, I don't have enough here, so I got to borrow from pardon me, the tens place, make this a 7, and then this becomes 11 because you're adding 10 to that ones place. Now I subtract 6 from 11 and I get 5. 5 plus 6 equals 11. Over here, 7 minus 3 equals 4. So 81 minus 36, 81 minus 36 equals 45. So I'm taking B equals the square root of 45. Remember, square root gives plus and minus, but we're only going to take the positive value. So square root of 45 equals, so I can square root that number 45, and that equals 6.708203932. So this is an approximation, but it's 6.708203932. And this is equal to the sine of theta multiplied by the radius. Okay? So the sine of theta multiplied by the radius equals 6.708 blah blah blah. Well, let's double check that, because you know we're kind of far afield now. What is the theta? Theta equals 48.2. Okay, so this equals 48. Actually, it was 48.1896851 degrees. So remember, our sine function takes in a degree value for theta, okay, and it outputs a length. All right, so let's take the sine, just the regular sine of the degree value that we found here. So we're going to take the sine of 48.1896851 degrees. Right? Now hit enter and you get this long decimal. Multiply that decimal by the radius of the circle or the hypotenuse of the triangle and you should get 6.708. So we're going to multiply this number right here by 9. And we get 6.708203932. Okay, which matches that. And just to prove this another way, now that we know what this value is, 6.708203932, Okay, we can actually use the arc sine of our angle, or rather of our opposite side over our hypotenuse length, and we should get the same angle. So this would be arc sine -1 inverse sine of 6.708 blah 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 over 9 should equal something really close to 48.1896851. So let me actually do that computation. Second sine, and then pull that value from your calculator since it has more digits, and divide it by 9. So this is the opposite length from the reference angle divided by 9, because 9 is the hypotenuse of the triangle or the radius of the circle. Close paren. Remember, we're going to get an angle because inverse sine or arc sine, arc cosine, arc tangent, the function takes in, it wants you to give it length measurements, and it's going to output a degree measurement. Okay, so let's see if it matches 48.189. Yep, it does. So we just confirmed that it's going to be the same, 48.189 blah 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 degrees. Okay, same thing for the arc tangent. Now that we know all these length values, we can do arc tan, second tan, and then divide opposite over adjacent. Okay, so we'll take our 6.7 length value and divide it by our cosine length, or our adjacent length of 6. Remember, tangent, this arc tangent wants you to give it the opposite side length, or the sine length, over the cosine length or the adjacent length, and that's what we're giving it, and it should output 48.189, and it does. So in each of these it's going to output the same value. That kind of gives us confidence that we've got not only the right angle, but that we've computed the right opposite side length. Okay, since we've computed the right angle, we could the correct angle, I should say, we can also compute this missing angle over here, since the total angle measurement of a right triangle is going to be 180. So we can subtract 90 for that angle, and then minus 48.2, or 48.1896851, 48.2, and that will give us, say, 180 minus 90 minus that angle gives us 41.81. Okay, just to prove something to those of you who are starting to catch on, now if I was looking here, if this was my new reference angle, and now I'm looking out this way, okay, I'm looking that way. This is now my opposite side, and here's my hypotenuse, there's my adjacent side. Everything switches now that I'm looking at this angle. So let's confirm that this angle is in fact 41.81 degrees. And let's do that by taking, well, let's see, we're going to take the opposite over the hypotenuse. All right, so let's take second. If we're using opposite over hypotenuse, that's the sine measurements. So we're going to take arc sine of 6 divided by 9. Okay, and we should get 41.8103, and we do. Okay, just to confirm that again, this is now the adjacent side length. So if I'm going to use the arc cosine, I'll take second cosine and then pull up that adjacent length, which we found before was that 6.708 number. I think I've got it up here in my memory, and divide that by the hypotenuse of 9. So this is arc cosine, gives me the same angle measurement. Again, if I'm going to use the arc tan to find the angle, Again, I'm just confirming and confirming all the way down. I'm going to take the opposite over the adjacent. Okay, so with respect to this angle, I'm going to take the opposite, which is 6, over the adjacent, which is 6.708. So let's do that. 6 divided by that value, 6.708, and we get the same angle. Okay? So that's kind of all the things that we can do with that problem. And we just verify that in fact it is 48.2. Okay. So all of these problems are worked in the same way, 1 through 8. You're going to end up using one of those inverse trigonometric functions, either arcsine, arccosine, or arctangent. If you know your Pythagorean theorem, you can always solve for the side you don't have, and you'll compute the angle. Now, numbers 9 through 12, which you can't see, numbers 9 through 12 give you the angle in one side length, and they ask you to compute another side length. Now, those are interesting, so let's do those. Okay, so let's do number 12, just in case the last one's the hard one. All right, so number 12 gives me this information. I've got this side here, which is 11, and I want to make sure that I end up with a right triangle here. Okay, and then that was the right angle, right? Yeah. Okay, this is the information I'm given here. So they actually provide this angle, which is awesome, 60 degrees. Okay, and they're basically saying, what is this? And they don't ask this, but we can find it. What is that? So again, we have to start by thinking of what are we doing here? What is our reference point? This is our reference point. Right? And before we do anything, we have to identify what the hypotenuse is. Okay, because the hypotenuse of this triangle is very important in order to know where to put our compass. So let's see here. I have a right angle over here. So this is the opposite side. Now we have two possibilities for our adjacent side. What is our adjacent side? This is our adjacent side. So is this. Now, I don't know, and it could be drawn wrong, but I think this is actually the hypotenuse, okay, or the radius of the circle. Like, here's what I think this thing is doing. And I might be wrong, but I think this is my radius. So I think this is actually looking like this. Of course, I could be wrong. Okay, just like that. So I think like this distance down here, if I connect it to the edge of the circle, I think this is the cosine. And I think this right here, this height, is the sine. Okay? But I'm really not sure. Here's what I know. I know that this is an adjacent side length. Okay, so you have to think about here. So if this is an adjacent side length, even if this is the cosine, I can use cosine in order to determine what it is. So I might actually be wrong. This might be, I don't think it is though, this might be the base, it can't be, it just can't be. This has got to be the radius of the circle. Anyway, that might actually be relevant. Yeah, this could be a hard problem. So let's think about our basic trig functions. We have sine, we have cosine, and we have tangent. Okay? So sine, let me put it this way. The sine of 60 degrees multiplied by a radius equals something. The cosine of 60 degrees multiplied by a radius equals something. It's going to give us the length, right? Now the tangent of 60 degrees multiplied by the radius equals something. What does it equal? This equals the opposite side over the hypotenuse. Cosine of 60 degrees times r equals the adjacent side length over the hypotenuse. Okay? And see, that's why hypotenuse and r, they're the same thing. And tangent is going to equal opposite over adjacent. Those are going to be those lengths, the quotient of those lengths, rather. Okay, so it's going to give us that quotient as a number. Okay, all these values, by the way, these values right here are going to be unit circle values. Right, so which one is the most appropriate for our problem? Well, you have to think about a right triangle. What is the hypotenuse of a right triangle? It is the side that is opposite of the right triangle. Okay? In other words, it's neither of the adjacent sides of a right triangle, ever. The hypotenuse, the longer side, is going to be the one opposite of the right triangle symbol. Okay? So this is the 90-degree angle. And that means this is 30 degrees right here, because 30, 60, 90. This is 30 degrees here. So in other words, what do we do to find these missing sides? Okay, if my reference angle is 60 degrees, what do I do? Because from the vantage point of 60 degrees, 11, that's not the adjacent side, that's the hypotenuse. So I think what this problem actually wants you to do I think it wants you to take the tangent value. Let me think about that. The sine of 60 times r equals the opposite over the hypotenuse. Okay. And cosine of 60 times r, which we know r is equal to adjacent over the hypotenuse. Okay, so it actually wants to know this side length. So in this case, oops, calculator turned off. In this case, and to think about it, I know what we're going to do. Okay, so we can actually find either. Look, the sine of 60 degrees multiplied by r, which we know is 11, is going to equal this. So we can find that real quick. The cosine of 60 degrees multiplied by r, which is 11, is going to equal this. So let's just do that real quick. Cosine of 60 degrees multiplied by 11 is going to give us this distance right here, 5.5. Okay? I don't know why my brain froze up there for just a minute. I was somewhat confused about what I was doing. All right, so now, like, let's just confirm sine of 60 degrees multiplied by 11 gives me 9.526. This is 9.526. All right. If we want to confirm that these values are correct, let's use Pythagoras. A squared plus b squared equals c squared. What should happen, okay, we want to know, does 5.5 squared plus 9.526 squared equal 11 squared? Okay, so let's see if that's actually true. What is 11 squared? Well, that's 121. So let's see if 5.5 squared plus this side length squared equals 121, and it does. So that verified that we found the correct side lengths. And indeed, from my answer key, x is 5.5. So this is really how you do this. I think let's do another one from this second section here, and that will kind of tie it off there. Let's take number 10, because this one's kind of look weird, weird looking angle. No, never mind. Let's do number 11, because that will give us something to talk about. All right, let's take number 11. Let's take number 11. Let's just draw it really quickly. Okay. So already you got to be thinking in your head, what's my 90-degree angle? Right there. Okay. And then what is the angle that is given to me? The angle that's given to me is this one right here, 50.1. Okay, so let me draw my little eyeball over here. There's my reference angle. So we are also given that this distance right here is 5. Now, just looking at this problem, it's not entirely clear what the sine, cosine, and hypotenuse or radius are. But let's look at it for just a minute. Think about a right triangle. The opposite side of the right triangle, that opposite side is the hypotenuse. So this is the hypotenuse. Which is, as we know, the radius of a circle. Okay? If that's the hypotenuse, with respect to our reference angle, this is the adjacent angle. So this is the adjacent angle, or side length. I keep saying angle when I mean side length. Adjacent side length, which is the cosine, okay, of 50.1 multiplied by the radius. That's how we compute that. And if that's the cosine, then this must be the sine of 50.1 degrees multiplied by the radius. Okay? So if we're going to draw our circle, put your pointy end over by the eyeball and make the diameter of the compass the radius of the circle, or the hypotenuse, and then draw your circle. Okay, so we see that we should rotate this a little bit in order to make it look like a proper trig circle, and you can dot dot dot, and that just kind of visually proves that this is the cosine and this is the sine. Okay, we already know this angle. We could find it by subtracting 180 minus 90 minus 50.1. That's 39.9. Okay, but we need to find these values. Here's how our triangle is presented on the page. Remember that if I want to find this value here, I am given the adjacent side length. So I'm actually given cosine of 50.1 degrees multiplied by the radius, or the hypotenuse, which I don't know, equals 5. Okay, equals 5. But remember what it equals. Remember what it's actually equaling. It's equaling the adjacent side length divided by the hypotenuse. Yeah, I'm not entirely sure that's true. I think I wrote it wrong. But anyway, let's take the cosine, and this is equal to 5. Okay, that's the key point, is that it's equal to 5. This might actually be wrong. I don't know. I'm going to leave it, peg it, comment on it later. Let me take the cosine of 50.1 in degree mode, right? And see what we get. We get 0.641. I see. This is my problem here. So let me write this out correctly, because I confused it. My fault. Moving too quickly. Okay, cosine of, let me write it again. Cosine of 50.1 degrees is going to equal the adjacent side length over the hypotenuse. Okay? Now if I take this whole thing, whatever this comes out to, and I multiply it by the radius, I'm going to get 5. That's what I meant to say earlier. Okay. The problem is I don't know the radius. So here's my situation. Cosine of 50.1 degrees multiplied by a number that I don't know, radius, is equal to 5. So let's just take the cosine of 50.1 degrees. Sorry. If I want to know what the radius is, I divide both the left and the right side of the equation by the cosine of 50.1 degrees. And then I'll have the radius equal to 5 divided by the cosine of 50.1 degrees. Okay, let's actually compute that. So 5 divided by cosine of 50.1 equals 7.79. Four, 8, 4, 4, 2, 9, 3. Okay. That is what the hypotenuse is. 7.794844293. Okay, so I could do one of two things here. I could use the Pythagorean theorem to find this missing side, or I could exploit the fact that we had this angle, this is a 90-degree angle here, so I was able to find that this other angle is 39.9, and I could now think of this as reference point 2, okay, looking out, and I could see that I know 5 there, right? So that's the opposite side. So let's do that. Let's say this. The sine is now the sine of 39.9 degrees multiplied by the radius equals 5. Okay, so earlier we were using the cosine of 50.1 degrees. Well, now we're using the sine of 39.9, because I know that the sine of 39.9 is actually drawing a new circle now if I do it that way, because now I got to put my pointy compass end over here by this eyeball and draw a new circle. It's kind of interesting. Okay, so now I've got a new circle, and this is my sine, and this now is my cosine for this brand new circle. So my sine of 39.9 multiplied by a radius value equals 5. So if I wanted to know again what that radius value was, I could divide both sides by sine of 39.9 degrees. So now r, we're going to try to find the same value again to verify it, equals 5 divided by the sine of 39.9 degrees. Let me take 5 divided by sine 39.9, and I get the same value. So that kind of proves to me that this is in fact the correct hypotenuse. We've kind of verified this. Okay. And I'm very tempted now to go on the sacred geometry tangent and divide it in two right here. Since this is a vesica, I'm tempted to divide that in two right now and compute a whole bunch of stuff. This is the midpoint of the line. That's interesting. We could find the midpoint there, but we'll stop. We'll stop that. Let's see. Did I find the side it wanted me to find? No. So here's the deal. Looking from the vantage point here at 39.9, if I want to know what this side length is, which I still haven't found, I want to know what this guy is. Okay. We can find him by saying, now remember, this is the adjacent side with respect to angle 39.9 or reference point 2. Check this out. So using the adjacent side formula, I'm going to be using cosine. So now cosine of 39.9 degrees times r equals that side length that I don't have, equals unknown. But I have r now. Because I have r, I can compute it. R is equal to 7.794844293. Okay, so I just kind of plug that in. Say cosine of 39.9 times 7.794844293 is going to give me 5.9799 The answer gives 6 right here. If you round up to the nearest ones place, you get 6. Let's verify that. Let me see if I spin this back to my original reference angle. There. Now I'm going to verify that this length is in fact 6. So now I'm working with sine because I'm looking at the opposite side. So I'm going to take in this example, because I'm at this reference angle and I'm looking opposite, I'm going to use sine of that angle, 50.1, multiplied by the radius of the circles, or the hypotenuse of the triangle, which is that 7.79 thing, and that should give 6, or something really close to 6. And again, it gives that same value, really close to 6, 5.9799. So in both cases, we're getting 5.9799, which rounds to 6. I don't know why they didn't just leave it as 5.98. I guess their significant digits are just 2, so they're rounding it to 6. Yeah? Okay. It's inconsistent. All right. This kind of demonstrates this whole thing about reference angles, because it really depends on from where you are looking what constitutes your opposite side and what constitutes your adjacent side. This last part of the video, maybe you should watch a couple times so you really understand what I'm talking about when I'm talking about the reference angle that you're looking at. It doesn't matter how this paper is rotated, but it does matter with respect to what you're calling opposite and adjacent, what you declare your reference point to be. Right? So just keep that in mind. That's why it's really helpful to use the compass and draw the circle out. Don't try to pack all of your thinking into that little space that's provided on the paper. There's no need to. It's just not worth it. So I think given this information, you should be able to do the rest of these on your own. If you have any questions, please post them in the comments. Otherwise, please like and subscribe. Thank you for watching.